Good afternoon, colleagues. Today I will present you our recent work on design and characterization of composite photoconverters based on cerium-doped eutectic composite of alumina and yttrium aluminum garnet and ruby for high power LED and LED white light sources. Solid-state white light sources are rapidly developing due to their high efficiency, long operation lifetime, and environmental friendliness. A particularly promising approach relies on blue LED OLED pumping combined with the cerium-doped eutectic composite of alumina and yttrium aluminum garnet converter. This eutectic composite material stands out for several reasons. Its unique Chinese script microstructure enhances light scattering, improves heat dissipation, and supports stable operation under high power excitation. It also provides high luminous efficiency and thermal stability, making it attractive for next generation lighting. However, despite these advantages, these converters still suffer from insufficient emission in the red spectral range. As a result, their color rendered IXth index usually does not exceed about 70, which is a clear limitation for application requiring high color fidelity. To address this issue, we propose to combine this eutectic composite with a ruby. The ruby introduces an additional red emission band around 680 to 710 nanometers, thereby improving color rendering index without compromising the thermal robustness of the system. This composite design also allows us to tune the spectrum geometrically by varying plate thickness instead of the relying on co-doping, which often leads to luminescence quenching. Eutectic were grown by horizontal direction crystallization with cerium concentration up to 1 atomic percent. Ruby was grown by the Vernel method with the chrome concentration around 0.2 atomic percent. Two parts of each converter were joined using a heat-resistant polymer resin, ensuring mechanical stability and optical transparency at elevated temperatures. Two types of composite converters were fabricated, which different only in the size of the eutectic plate. The ratio of the area of the eutectic and the ruby plates in the composite converter was 1:1 in type 1 and 1:2 in type 2 converter. As a result, we got the chromaticity coordinates of both converter types lie close to the white point region. Type 1 shows a shift towards warmer white, while Type 2 tends to cooler shades. Type 2 converters exhibit a higher luminous efficiency and color rendering index, with slightly lower colorated color temperature, compared to Type 1. For instance, the configuration Type 2 converter with 0.3 mm ruby and 0.3 mm eutectic plate provides luminous efficiency about 170 lumens per watt, color rendering index around 79, and colorated color temperature near 6000 Kelvin. In summary, the cerium-doped eutectic composite of alumina and yttrium aluminum garnet is a highly promising base material for light converters, offering superior thermal and optical properties. By integrating it with ruby in composite structure, we successfully improved color rendering while maintaining high luminous efficiency. Thank you for your attention.